Hi, I'm Darsh,
Hi, I'm Bella.
and we're bringing you LL-laMmps. So, with our project, the idea is to automate some parts of a molecular dynamics simulation. So, molecular dynamics is a powerful computational tool to simulate atoms and the way they move using Newtonian mechanics. And this has wide applications in chemistry, biology, material science, and physics. So basic workflow for an MD simulation using a software like LAMMPS looks like this. So firstly, the scientist creates a research question and an experimental design that can be simulated. And the two main types of files that are created here are the data file, which contain the structure and the bonds, so where the atoms are arranged and how they're connected, and the force field parameters, which define how those atoms move around. And secondly, the input file, which describes the environment that the atoms are in, and also the simulation specifics, such as the time it's going to take and what the time steps are of the simulation. So all in all, you can take those input files, plug them into the software like LAMMPS, and the output provides you with some new scientific insights. So our plan here is to automate that setup part in three different sections. So starting with that research proposal, then the two different input files that we need. So the first thing we're automating is that idea and experimental design generation. So the user submits a simple query to our multi-agent model here, which is a group chat formatted system. So it's a lot of agents that can autonomously select when they speak. So we have the planner that leads the entire group, the engineer, which has access to papers on the web, such as archive API, and then the scientist, which can take a summary of those papers and then create a research proposal. And lastly, we have the critic, which polishes over the research proposal. And so we can have multiple iterations of this, so it's refined. And at the end, we have a research proposal that has the hypothesis, problem statement, and even things like the expected outcomes.
So once a research proposal has been completed, we can begin to create a data file. And so this pipeline is a sequence of agents, starting with the MD mechanism agent that expands on the research proposal's relevance to MD, structured expert agent, and a parameter expert agent that suggests where to get those structure and parameter files, pre-processing agent, which decides in what order certain simulation software like VMD and topo tools should be called in order to create the final data file. And lastly, a simulation caveats agent, which predicts what possible errors might come up along this pipeline and also during simulation as it relates to the research proposal. And so at the end, we'll have a complete protocol for any beginner to create a data file, which generally in MD is the biggest bottleneck to beginning an MD simulation. So once we've created the data file, we can create an input file generation pipeline. And this is really well suited for multi-agent systems because now we don't need to call on any other external software. We just need to create a very strong structured output. So we begin with an analysis agent, which decides what the simulation environment should look like. And we found that the output is generally much stronger when we begin with a pseudocode, which then passes along that pseudocode to a script writer, and then a critic agent, which finalizes and perfects the final script. We also include a digest agent, which creates an output of explanations for how and why the input file was created. So here's our code. We begin with a summarization phase where, given a user idea, very basic collagen interactions with titanium surfaces, for example, a set of agents are called in a group chat to create code to call an archive API and get a set of papers that are relevant to this idea. And so with those ideas, a discovery agent creates a novel idea based on those papers and outputs a valid JSON with problem statement, hypothesis, expected outcome, etc. We can now move on to the simulation setup phase where we create a data file. Agents are called in order, starting with the MD mechanism agent, the structure expert agent, the parameter expert agent, the pre-processing expert agent, and the simulation caveats agent. Lastly, we can move on to the input file generation phase. And so we begin with another set of agents, starting with the LAMMPS analysis agent, which decides what the simulation stages should look like and different conditions for the input file. We then create a pseudocode agent, which creates a structured ordering for the LAMMPS file. the scriptwriter agent, the critic agent, and the final digest agent.
So let's see what that code output. So firstly, we have the research idea that was created by the first group chat of agents, which includes the problem statement, hypothesis, the mechanisms of the experimental design, and also the expected outcome. Secondly, we have the simulation plan, which is from the second sequential agents system, which tells us how to create the data file. And it includes references to other tools such as VMD and Topo tools and where to get those structural and parameter files. And lastly, we have, I'll show the pseudocode first of the input file, which goes over all the environmental conditions and the simulation setup that's needed. And then finally, that pseudocode's turned into a real input file that can be input into our software. So what we've done here is fully automated the setup for a LAMMPS simulation, and this can help beginners jump into MD a lot faster. So for the future work, we're looking at expanding our scope by interacting with other tools that are used in MD automatically. So starting with the data file generation, right now we just have a protocol on how to make it ourselves. But if we can get the LLMs to do it entirely by interacting with topo tools and VMD, that would be great. So secondly, with the execution agents, once it's time to run the simulation, rather than the user taking that output and running the simulation separately, if we can just directly run it for the user using high performance computing, that would be a good next step. Thirdly, analysis agents. So once the output is ready from the MD simulation, we want the LLMs to interpret the results and give a little summary. And lastly, Copilot for error handling. So as that simulation is running, the LLM model should be able to detect the issues that are happening, refine the scripts, and then run them again. So the key insights that we learned were the difference between the sequential agents and group agents and when to use each one under what context. Secondly, using pseudocode and critic agents to refine our output has been very beneficial. And then using agents to expand ideas and brainstorming. And lastly, prompt engineering and in what order to queue certain prompts and how that's helpful to get the result that we need.